Hello everyone, and welcome to the short paper session number 1, all about rendering. So we have 4 presentations, and you can post your questions during the video presentation or right after, either in the YouTube channel or in the Discord, which is even better. So we'll start with the first presentation, the paper Accelerated Foveated Rendering Based on Adaptive Tessellation, which will be presented by Ankur Tiwari.
In this session, today, I would like to talk about a research topic, accelerated foveated rendering based on adaptive geometric tessellation. Our perception of the world is based on what we see, and it took us quite some time to get to this stage. Likewise, computers and display devices have evolved dramatically. The space and processing capacity is limited, so there is a need to devise optimization techniques. We took one such scheme, adapted from nature, foveated rendering, and tried to further enhance it, again, by looking at nature. Saccadic suppression is a topical area of research, and our algorithm implements this very concept to enhance foveated rendering. This presentation has several subsections. We will begin our discussion by breaking down, or deconstructing, the project title into keywords, explaining their significance. The section also covers the motivation behind pursuing research in the sector. Moving on, we get to a demo section, which is the output of our work. Subsequent slides have covered what actually goes on in the background, all the technical details. A short video clip also depicts the background story, but more on that later. After displaying and briefly explaining the functioning, we will move on to the performance aspects of our algorithm. The section after this will cover details of our user study and its nuances, followed by the results of our experiment. Finally, we shall briefly discuss the future of this work and related areas of research. Let's move on to analyzing the title of our work. This research topic can be broken down into 3 subtopics to grasp its meaning and significance easily. The first keyword is accelerated. Our algorithm uses a shader program to allocate some work to the graphical processing unit. The process is a form of hardware acceleration. The second key phrase is foveated rendering. If you observe the image on the left, you will notice concentric circles with increasing radii in a purple color. This is a depiction of the output of foveated rendering. The camera, just like a human eye, focuses on a very small region. This cone has a very small angle, and the resolution of the image lying in this region is very high. There is a progressive degradation in resolution on moving away from the focus point. But why does this happen? The answer lies in the construction of the human eye. Our eyes have photoreceptors called rods and cones located on the retina. The density of cones near the center of the eye is much higher than the density near the periphery. Fovea centralis is the biological term for the region with the highest cone concentration, as a consequence of which it is also the region for the highest visual sensitivity. The diagram shows the relative acuity of the human eye against the horizontal angle from foveal vision. Notice the sharp drop on either side of the fovea. The horizontal visual field for each eye is large, but the foveal region, however, subtends only a 5-degree angle, the foveola subtending up to 1.2 degrees horizontally. We will now talk about saccades and fixations. Saccades are rapid eye movements which align the fovea with the region of interest for the best resolution of spatial details. During the motion, a saccadic suppression occurs, which is the phenomena where the sensory information is significantly reduced. When the eye pauses at a location or fixates, details are registered. Saccades can be of any length from 20 to 200 milliseconds. The minimum time required for the eye to make sense of the input is 100 milliseconds, making the minimum time required for the entire process 120 milliseconds. Now, a short video clip will be played. Orange spots will appear on the screen in a random order. Move your eye to the location of the new spot. Try not to look anywhere else. Did you notice how your eye was moving in a jerky motion? This is how saccades and fixations occur. The third key phrase is adaptive geometric tessellation. Tessellation is the arrangement of shapes closely fitted together, especially polygons. Our application used quadratic approximation of subdivision surfaces. The implementation was done in the tessellation control shader using the OpenGL rendering pipeline. Now, we'll see a demo. The mouse cursor has been used in our application to depict case location as a proof of concept. Keep looking inside the red viewing box at all times. The following section will explain the method and implementation. We are using the cursor location as a substitute for the gaze location. As the cursor moves around the display, we process its coordinates. The cursor gives us the viewport space coordinates. They are then transformed into the normalized device coordinates. Further transformation occurs to the homogeneous clip space coordinates and then the camera space coordinates. The application then casts a ray through the cursor location. This ray is normalized and passed to the tessellation control shader. Our tessellation method uses triangular patches. The perpendicular distance of the ray from the vertices is calculated. The final tessellation value is calculated based on this distance. We will now see a demo with a wireframe model to see what happens in the background. On zooming in to the model, we can see how the number of triangles is changing as the cursor changes location. The next section explains the saccade fixation implementation. For now, we are considering a display which updates at a frequency of 120 Hz. The time required for each update is therefore 8.33 milliseconds. In a normal situation, the updates and the corresponding tessellation value calculations will occur at this rate. During a saccade, however, due to saccadic suppression, it is not possible to see what's happening on the display, leaving the constant screen updating to be of no use. Our solution is to update the screen as soon as the saccade is initiated. We calculate the velocity of the motion and predict the possible location of fixation at the minimum time interval for a saccadic motion. The process is reiterated in case the cursor is still moving after this time interval. In case a fixation occurs, the contents of the screen are not updated. Therefore, selective updation reduces the number of calculations required significantly. Now consider that a saccade and fixation occurred together. The minimum time for a saccade is 20 milliseconds and the minimum time for a fixation 100 milliseconds. The minimum total for the whole process, therefore, is 120 milliseconds. During this time, the screen will be updated around 14 times for a 120 Hz display. By updating the screen only once, at the initiation of the saccade, we reduced the number of required calculations by a factor of 14. It is evident that the factor will further improve for displays with even higher refresh rates. Fixations generally occur for longer durations, therefore improving the performance by an even larger factor. As explained earlier, the update happens as soon as the saccade is initiated. After the minimum time interval, the program checks if the saccade is still occurring. However, if the saccade got completed in between two consecutive checks, the predicted location might have an error. This is compensated for by providing a slider in the user interface to adjust the radius of the highest resolution. The minimum resolution in this region can be made sufficiently high to make up for the error, if any. We will now talk about the user study. The experiment consisted of 15 participants, and each one of them underwent 3 trials. The successful result meant that the participant could not differentiate between the regular tessellation and our implementation. Each participant was first given a questionnaire assessing if they knew about foveated rendering. A query regarding their eyesight was made to ensure that they could manage to participate in the experiment without issues. After the task was explained, each participant was seated approximately 60 centimeters from a 15-inch backlit LED display. First, the video with dots, which we encountered earlier in the presentation, was shown. This was done to familiarize them with the task they had to perform. 3 videos were shown to the participants. The first was a regular subdivided model with no optimization. The second had foveated rendering without the saccade fixation implementation. The third video ran our algorithm in the background. Each video had a viewing box, like the red box we saw earlier moving around the screen. The box performed 2 types of motion. One was a smooth motion around the model. The second resembled saccades and fixations. After each video, a still frame with 2 viewing boxes was shown to the participant, asking them about the difference in relative quality of resolution. The result was interpreted by using the video with regular subdivision as a benchmark, since we knew nothing was happening in the background there. The viewing box was a square with 2 cm side length. The amount of tessellation for the models was measured based on the number of triangles generated. For example, a coarse model of a few hundred polygons, when converted into a model with 1 million polygons, the density of the latter has been used for comparison. The model on the top left is a 100,000 polygon model. The image below it shows a zoomed in snap. The model in the middle has 1 million polygons, and its corresponding zoomed image is shown below. For our videos, the distribution of mesh density was arranged so that there existed a 1 million polygon model density at the gaze location. The density at the periphery, however, was that of a 20,000 triangle model. The results of the user study have been discussed in the following section. Out of the total trials, in 2.5% of the cases, users reported unwanted visual artifacts on the screen. 6% of the trials for the first video had this issue, whereas for the third video, the problem was reported in only 1% of the total cases. Since the first video had nothing happening in the background, artifacts could not technically occur, as nothing in the model actually changed. This leads us to believe that the issue was primarily due to the experiment technique owing to the unavailability of a gaze tracking equipment, rather than the functioning of the algorithm itself. Since the distribution of tessellation was controlled to limit the maximum number of triangles to be less than 8 times a fully tessellated model, the improvement over a complete saccade and fixation compared to a standard tessellation model was by a factor of 112. The natural successor of our work is implementing the algorithm on an actual eye tracker. New issues pertaining to the hardware dynamics, the latency, accuracy of the hardware, and the user comfort will come up and subsequently will have to be resolved for a market-ready product. Further research may be carried out in various sectors, which were pieced together for this project. A primary contender is combining this algorithm with other adaptive tessellation techniques, such as those based on proximity, or the orientation of the 3D model to the camera in the scene, or those based on the curvature of sections of the model. Models for predicting the fixation site can be explored as well, and the incorporation of other eye movements, such as microsaccades and smooth pursuit, can be done. Thank you for attending this session. We would love to hear your feedback on our work.
Okay, thank you, Ankur, for the very nice presentation. We'll start the Q&A. If anyone has questions, please post them in the YouTube chat or in the Discord channel. I'll start with a couple of my questions. So in the results, you talk about some artifacts that were perceived in the first video. So I have two questions about this. Did you actually shuffle the order of the videos, or were they presented always in the same order?
The second and third videos were often shuffled because the first was a benchmark, so we didn't move that anywhere, but the second and third videos were often shuffled around.
So this could be due just because the first one was always shown first to the subjects, for example?
It was necessary because we knew nothing was happening in the background, and we needed people to get used to the system which we're using for the experiment.
And did they report what kind of artifacts they were actually perceiving in the videos?
So when in the later stages, when I showed two viewing boxes, and I asked them to check the differences between the two viewing boxes on the image. So that's when they were supposed to they were not supposed to see the other side of the image because I told them to focus inside the red viewing box. But sometimes the eye would obviously stare out of the region, which will not happen in an eye tracker because that will be the location where you're actually looking.
Okay, because you were actually inducing the saccades by the box. Okay, and then how would you actually detect them in a real scenario where you have the eye tracker? What actually characterizes a saccade that you could say, well, now I have to take in consideration saccade?
So there are a few eye trackers which already implement foveated rendering, but saccadic implementation, I don't think I've seen that anywhere till now. And especially in the tessellation, using geometric tessellation. A few things which we have to consider is that there will be some lag because of the device itself, which is the primary factor. We're actually working on it right now. And that's basically the hardware dynamics which we're talking about.
And is this lag in the same magnitude as the actual phenomenon you're looking for, or is it much less?
Again, we have not really tested it, so we don't know, but there's going to be the eye tracker works at a different frequency. The screen works at a different frequency, so there's going to be some mismatch.
I have one last question. If you render, is there any overhead from tessellation, from the online tessellation? I mean, if you get the full model and just render it without any tessellation, do you get the same timing as tessellating it in real time?
Yeah, there's no overhead involved. Nothing really changes because again we're using just one model with a very limited number of polygons. Again, if you have a whole scene, things will be very different.
Okay, well, if there are no questions for the audience, I'd like to thank you and your co-authors again, and for the very nice presentation and nice paper. Thank you. So now we move on to the second presentation, which is a photomapping superluminal particles, which will be given by Gustave Aldermarchon. I hope I pronounced that correct.
Hello everyone, and welcome to this presentation. Here, I will present our work on photon mapping superluminal particles, something we use to visualize the Cherenkov effect. But first, I think some introductions are in order. My name is Gustav Almarsson, an industrial PhD student at the Lund University Graphics Group and employee of ARM Sweden. This also happens to be my first paper submission, so it undoubtedly have a few rough edges, and recording this virtually from home is also a challenge in itself. But like all of us these days, I will make the best of it and try to present everything as clearly as I can with the resources that I have. As you all know, the world is full of many weird lighting phenomena, from auroras to zodiacal light and everything in between. And many of these are regularly simulated in the field of light transport. One phenomena, though, that to our knowledge haven't been simulated before in this context is the so-called Cherenkov effect, the eerie blue glow often seen around nuclear reactors. I first got this idea after watching the Chernobyl miniseries last summer, where the eerie blue glow seen around the power plant is attributed to the effect. While that is technically incorrect, the light shown in the series is actually caused by a phenomenon known as ionized air glow. But the effect is real enough though, and can be readily observed around nuclear reactors submerged in an optically dense medium. Here you can see a few examples of it from the Reed Research Reactor and the Advanced Test Reactor respectively. Physically though, as a charged particle, such as an electron, moves through a medium, it will interact with atoms of the medium and emit electromagnetic waves as a result. According to Huygens' principle, these waves will travel outwards spherically with the medium phase velocity, or the speed of light inside of that medium, here denoted as cm. Normally, for a particle traveling with the velocity vp, the spheres we mentioned earlier will bunch up in the travel direction of the particle, but otherwise they will not cross. However, the only physical limit to the velocity of a particle is the speed of light in a vacuum. Hence, inside of media where light itself is slower than that, it is possible for the particle to travel faster than light. And when this happens, the spheres we mentioned will begin to cross and will start to constructively interfere and consequently generate coherent photons at an angle proportional to the particle velocity. Structurally, this is very similar to how a sonic boom is created for supersonic aircraft, but with sound waves rather than photons. Additionally, with some simple trigonometry, it is possible to compute the angle of which the photons will be emitted. At a more detailed level, however, the way the energy of the particle is distributed is governed by the so-called Frank-Tamm equation, which will spread the energy over the electromagnetic spectrum. Normally, the equation is given on this form, where Q here is the electric charge of the particle, omega is the angular frequency of the photon, and mu is the permeability of the medium, that is, how easily a magnetic field is induced inside of it. In our case, we're mostly interested in how the particle energy transforms into a color. So first, we want to rewrite this equation in terms of wavelengths, which eventually gives us the equation on this second form. In this case, we have folded several of the values inside a single constant here, alpha, something that is known as the free structure constant. Also, I should note that our goal with this is to map particle energies to colors, so we can be a bit liberal in our interpretation of this equation. And since it would be rather difficult to assign physically correct permeability functions for all media in a renderer, we're going to assume that mu is equal to 1 for this work. This is a rather extensive simplification, and a more accurate simulation would need to take this factor into account. When doing this, though, it is straightforward to visualize the Cherenkov radiation spectrum as shown here. Here, we can clearly see why the effect is so brilliantly blue in color. As the curve is exponential, the largest energy output that we can readily perceive lies in that particular region. The way we simulate the phenomena, though, was by extending the stochastic progressive photomapping algorithm with an additional pre-processing step. We trace the charged particles from predetermined sources in the scene and store the paths that these traveled. This way, the particle paths effectively becomes light sources that can be sampled like any other, albeit with a slightly modified sampling scheme. First, we choose a random point somewhere along the particle path. Then, we find the particle velocity and the refractive index at that point, and we use that information to determine if the particle was superluminal at that given point. If that was the case, then we set the photon direction to somewhere inside the Cherenkov emission cone. Otherwise, we set the photon direction to a uniformly spherical direction instead. And finally, we evaluate the Frank-Tam equation and use the resulting spectrum as a photon color. And then we simply trace the photon as per usual in SPPM. Since our photon mapping algorithm is a Monte Carlo simulation, however, it is often desirable to know the probability density for the function being evaluated so we can perform importance sampling. For photon mapping, this means we want to know the photon probability density function, that is, the combined density distribution for the photon origin and direction. For our particle light, the photon origin and direction are independent, so the combined PDF is simply the product of the density and the origin respectively. Of these, the origin density is straightforward to compute. It is simply 1 over the total particle path length, as the photon will always start from somewhere along this path. The photon direction, though, is slightly trickier to compute, as our direction can be either entirely random or within the Cherenkov emission cone. To do it, we define our probability mixing model as follows. Here, S is the probability of the particle being superluminal at any given point along the particle path, and PC and PS are the probability densities for a uniform direction somewhere in the Cherenkov cone and uniformly in a sphere, respectively. These values, though, are readily known as 1 over 2 pi and 1 over 4 pi, respectively, and plugging these in yields the final directional density as this. Also, if it is possible to find all intervals where the particle is superluminal, the probability can be computed as the superluminal path length over the total path length. The algorithm we just described have been implemented in PPRT, where it is implemented as a new kind of area light source. I was originally hoping that the code would be available in GitHub in time for this presentation, but it has unfortunately been delayed. Nevertheless, I've included a link here to a GitHub repository that will eventually contain a copy of the modified PPRT code. I should note, though, that the PPRT version of the algorithm works slightly differently to the algorithm we just described. During the PPRT pre-processing pass, we emit the charged particles as random rays that penetrates everything in a straight line. This is implemented by continuously performing ray intersections along the same direction and recording the intervals where the particle turns superluminal. Then, when sampling the light, we use an additional random variable in order to determine which of the particles to sample. I should note, though, that this requires a minor change to the photon density function to account for this. Other than that, the algorithm works precisely as described before. Done this way, it is straightforward to add the particle light into any PPRT scene, as you can see in this partial PPRT file. We simply specify that this disk should be turned into an object that uniformly emits charged particles. And this also allows us to specify some parameters for the particle source, such as a desired number of particles to emit or the velocities they should have. In this case, we're using a velocity scale from 0 to 1 based on the absolute speed of light in a vacuum. So in this case, the particle is emitted at 80% the speed of light. So with all of that, it's time to get into some of our actual renders. First up, we wanted to simulate the effect in a very simple setting, such that we knew roughly beforehand what the resulting image would look like. In this case, we created a variant of the Cornell box with a particle emitter on one wall with an optically dense medium right in front of it. We also wanted the walls to be entirely colorless, so that any perceived color were that was given by our modified Frank-Tam equation. In this case, we would expect light to be generated from inside of the sphere and travel in the Cherenkov emission cone, forming this cone you can see along the far wall, here depicted with the dotted lines. And running this through our modified PBIT algorithm yields an image that looks something like this. At first glance, it looks more like there's a light source over here on the left wall. However, there are some telltale signs that our algorithm is working. For instance, if we look at this spot of caustics and even this shadow up here, then it's clear that light must be coming from the right wall, even if that light source isn't directly visible. Moving on to something slightly more complex, but staying with the Cornell box. This time, we want to see how varying the refractive index changes the Cherenkov emission angle. This time, we place a small particle emitter in the center of the box and a number of cylinders with varying refractive index in a semicircle around it, as depicted by this image. And we'll let the refractive indices range from 1.25 up to 1.6. This time, our render comes out something like this. And this is roughly what we would expect. For cylinders with a rather low refractive index, the emission cone is very shallow and then gradually gets larger as the index of refraction increases. One thing that is quite interesting to see too is to see that the total internal reflection starts to come into effect here, giving us these interesting caustic patterns here along the walls and the roof of the box. For our final and most complicated scene, we wanted to connect back to where Cherenkov radiation normally occurs, that is, inside of nuclear reactors. For that, we took this photograph from the Reed research reactor and created a virtual 3D model of it in Blender and exported that to PBRT. Here, we placed particle emitters inside of the fuel rods in a configuration that is similar to some real nuclear reactors. Doing all of this gives us an image that looks something like this. Clearly, we get something that looks like a reactor. The mass of Cherenkov photons coalesce into a rather uniform glow around the vessel. It is, however, quite different from the photograph we showed earlier, as we can see in this comparison. We're not entirely certain why it differs so much, though. There are, of course, a large number of things that differs from the setting of the photograph compared to our renderer. To name some of the issues, the optical distance between the reactor and the camera is actually quite large, so there should be quite a bit of light scattering happening inside of the water tank. But as the renderer is only considering surface photon mapping, this is not being taken into account. And, as we mentioned earlier, we're not modeling some potentially important parameters, such as medium permeability. No, naturally, a more accurate renderer would need to solve these kind of problems. I should note, though, that in practice, it is often easier to fake the brilliant blue light from the Cherenkov effect with conventional virtual light sources. But as we demonstrated with PBRT, it is possible to implement it as just another kind of light source. Furthermore, there may be cases when we want to simulate the effect accurately, such as for generating reference images. Also, Since the effect is used in radioactivity detectors, it may be of interest to use this to figure out where to physically place these kind of detectors. Also, there is some work in the field of medicine to use Cherenkov radiation as a complement to our other methods, or as a completely new in vivo imaging technique. So ray tracing could potentially be used to accelerate or improve their methods. As mentioned before though, this is still some rather early work so far. There are quite a few directions we are thinking of taking this. For starters, the particle paths in this work were all modeled as straight lines. In reality, charged particles often change propagation direction after each interaction, so it may be of interest to model the particle paths as more of a random walk instead. Also, we only consider the Cherenkov effect in this work, but there may be other phenomena that we haven't considered that could be modeled in a similar fashion. Most crucially, however, this work was exclusively based on surface photon mapping, as that seemed like a good place to start. In reality, Cherenkov radiation is seen as more of a volumetric effect. As such, it should be analyzed in a setting where that can be taken into account. Finally, to conclude, in this work, we created a small extension to the photon mapping algorithm that allows us to visualize a phenomenon from nuclear physics that typically only occur under very specific circumstances, namely the Cherenkov effect. This was implemented in the well-known physically based renderer PBRT, where we were able to produce convincing images of the effect, albeit without volumetric effects. Additionally, this work also shows that it may be possible to simulate other phenomena from nuclear physics or even from medicine. This is some rather early work though, and there is still quite a few areas left for us to explore in the future. But that is all the material I have for now. Thanks all of you for listening. If you have any questions, feel free to ask them during the Q&A session after this, or by contacting me directly. Thank you.
Thank you, Gustav, for your very cool presentation. For the audience, please do not hesitate to post your questions in the YouTube chat or in the Discord channel, or to send your virtual applauses to the authors. I have a couple of questions to start with. So, in your future works, you talk about the volumetric effects that you're not handling so far, right? Which probably will make your image, especially for the reactors they are inserting some water medium, look more like the real thing, right?
Yes,
but if you do model the volumetric effects, do you still have to consider, for example, random walks to replace a straight path, or would that already take care of this part?
We don't know actually. It might be taken care of, and hence we may not actually have to care about that part. That's stuff that remains to be tested.
And you also mentioned some other effects that you might have to consider. Do you already know which are such effects for a more complete simulation of the...
Yes, there's actually quite a lot of nuclear effects that happens at that level. For instance, the distribution of nuclear particles isn't actually as even as one would expect. For instance, the energy is often distributed between a neutrino and an electron for the typical particles that generate Cherenkov radiation. So there's a lot more effects that could be handled in that particular case.
Okay, so I also noticed that searching randomly for some image of reactors, that some, well, as you showed, some are not really blue, but more in the purplish color. But I also saw some that were actually the green spectrum. Is that something from the camera effect, you think, or was just the way the photos were generated?
I think that's more as an effect of the camera itself. I've never actually seen the effect being greenish, but I guess that can happen if there is some scintillation happening, forcing the solar radiation or the scattering to happen at an earlier wavelength.
Okay, thank you. If there are no more questions for the audience, I'd like to thank Gustav again for the very nice presentation and very nice work also. Thank you, Gustav.
Thank you.
So now we move on to the third presentation, controllable caustic animation using vector fields, and the presenter will be Irene Baeza.
I'm presenting our short paper called Controllable Caustic Animation using Vector Fields. This work was developed together with Markus Gross and Tobias Gunther in the Computer Graphics Laboratory in ETH Zurich. To begin with, what is a caustic? Light transported from an emitter through a specular object and to diffuse surface can create complex and interesting light structures that we call caustics. We can find beautiful caustics created, for example, by the water surface, like here on the left, where we have a real image of shallow waters where caustics are created on top of the sun, or on the right, which is a render image of the bottom of a swimming pool. But in general, any specular object illuminated by a light can create these effects, for example, a glass on a table. So we can create very interesting, complicated, and eye-capturing scenes by placing specular objects and illuminating them in specific ways. Now, rendering caustics is not trivial. In fact, it's very challenging to estimate the irradiance with unbiased methods like path tracing, since it's very improbable to sample such paths. In this paper, our goal is to animate caustics artistically, which is the light editing problem. Thus, we aim to provide an intuitive and precise tool to create artistic directed caustic animations. The caustics are thereby meant to break the physical constraints of geometric optics, allowing, for instance, fluid-like patterns. Our method enables complex caustic movements, which could be used, for example, in marketing or visual effects. Other biased methods, like photon mapping, are more efficient to render this type of light behavior, and that's what we use in this paper. Photon mapping is a two-pass algorithm. First, it starts with the photon tracing. If we have a scene like this one, with a light emitter somewhere, we start emitting photons to the scene that we scatter and store in a data structure called the photon map, where they hit a diffuse surface. Then, in the density estimation step, for each shading point, we take the closest photons given by certain chosen radius and approximate the radiance using their density. The most interesting thing of this method for us is that we can separate the global illumination photon map from the caustics map, where we only store photons that have gone through a specular surface. There are many papers about artistic light editing in a scene, or caustic synthesis, where, for example, they find how the specular surface should look to create a desired target image. Also, other work focuses on artistic control in fluid animations of smoke and liquid. In this paper, our goal is to animate the caustics of a scene and blend them into a desired target image. Related to this, previous work by Gunther et al. Formulated the same problem in their paper called STLS caustics. The way they formulated the problem is as follows. First, their method establishes a correspondence between source points in a set A and target B, where the source points are the caustic photons previously projected into a 2D plane, and the target points are taken from important sampling a target image. They construct a bijective map solving an assignment problem by minimizing a discrete energy that enforces both short paths between source and target positions and preservation of local neighborhoods. They use a greedy algorithm to find a local minima, but since this step is costly, they only use a small subset of points to generate a partial assignment and then interpolate using thin plate splines to create a set that is close to the target position speed, but still contains high-frequency details, so resembles a caustic. Finally, They use the refinement step where they find the farthest closest point and does an assignment from the intermediate set of points I to the target B. Then, they blend the photons between the linear paths from A to B and the path I that preserves the original caustic patterns. The results look like this. We can see that intermediate frames also resemble caustics, but they get a ghosting effect due to the crossing paths of photons towards the end of the animation. This method also requires tedious and indirect parameter adjustment to avoid unwanted movements in the blending. To avoid ghosting effects and gain more control on the animation, we reformulated the problem. Since our goal is also to create a target-driven caustic animation, we used the initial bijective map from Gunther et al. To map the source photons with the target image. However, we described the trajectory of the photons as if they were moving in a flow. The path that the trajectories will follow is highly nonlinear, because the flow also follows constraints set by the user, such as the direction in a certain area or a non-crossing wall. This means that the flow changes through time, and thus we solve the problem at each time step. We want to compute a smooth transition animation from a source caustic to a target image that is controllable by the user. For this purpose, we construct a vector field with the following goals. First, controllable divergence and rotation. This gives the user freedom to choose between a smoky look and a more linear and compressible flow in the animation. Guide to target. The vector field has to carry photons from their source position to the target destination. Follow directions. The user should be able to draw guidance trajectories that the photons should follow. No wall crossings. The user can place walls that the photons are guided around. The smoothness gives the flow a consistent movement even when no constraints are imposed. And finally, turbulence. It should be possible to create turbulent motion synthetically. We divided our system in three main steps. First, the photon tracing. Second, we compute the photon animation, where we set constraints and blend photons. Finally, we perform a progressive photon mapping rendering to obtain the final keyframes. I will go over each stage and give a brief overview of them. So let's start with the photon tracing step. The input to our method is a 3D scene that contains at least one specular surface. We render the scene using photon mapping, from which we obtain a background image that will be used in the final rendering to speed the process, and the caustic photon map, with the positions and flux of the photons that are used as initial positions of the blending. Once we have the initial photons, we now perform the photon animation. This step contains our novel method for the artistic blending of caustics. We compute the vector field by feeding a stream function and a scalar potential to a set of constraints. Using a weighted combination of the cogradient of the stream function and the gradient of the scalar potential, we obtain the desired vector field. Note that the cogradient of a string function is always divergence-free, and that the gradient field is always rotational. This let us fulfill the first goal, since the weight gamma gives artistic control, as it allows the user to balance between a divergence-free solution, when gamma is 0, which behaves like a fluid, and a rotational solution, when gamma is 1, which acts like a gradient flow. The first step on this pipeline is to match the source points to the target points. We had obtained the source points as the photons from the photon caustic map in the previous step. Before the matching, we separate them depending on which specular object or light has created them. Then, each caustic can be treated individually. Let's take the photons of one caustic as the source points A. Given a desired target image, we use the importance sampling to obtain the set of target points B, where the size of the source and the target point set is the same. Then, we construct a bijective map that assigns to each source point a unique target position by solving Gunther et al.'s assignment problem. In order to find the stream function and vector potential that will guide the photons according to our needs, we discretize the 2D domain in a 2D grid. Since we know the one-to-one correspondence between the source and target positions, at each frame, our photons have a guidance direction that assumes a direct linear path between them and is scaled by the total length and time t. This constraint fulfills the second goal, guide to target. In order to fulfill the follow direction and know while crossing goals, we introduce two types of user constraints that give us control on how photons will move in the resulting animation. First, we introduce directed lines, which are lines that the user draws on the grid and will determine, for the chosen set of frames, the direction of the photons in those grid cells. Second, wall lines. We want to place boundaries across which photons should not move, and that will force the flow to move around. To do this, we first detect the photons that are close to wall areas by defining the convex hull of the walls. In the example image, we can see the wall line in pink and its convex hull in green, where the thickness of this area is a parameter that can be chosen by the user. So, if we have again the current position and the target position, we can find the shortest path between them in the graph. We then use the current vertex and the next vertex in the path to compute the new guidance direction, which is also scaled by the total length and the time t. With all the constraints of each photon at each frame, we construct an energy minimization problem where we also add a smooth term to fulfill our smoothness goal. For more details on the discretization of the quadratic energy and the resultant linear equations after minimization, please refer to the paper and additional materials. Finally, we construct the vector field of that frame using the obtained stream function and vector potential. We numerically adapt all particles in the vector field to the next time step using a fourth-order Runge-Kutta integrator, which models the trajectories as tangent curves of the vector field. When the photons are close to their target, we delete them from the optimization and blend them linearly until they perfectly reach the target at the end of the animation. We distribute the total source flux uniformly across the target locations by computing its average and blending it linearly through the animation. Finally, now that we have the positions of the photons at each time step, we only need to render the final keyframes of the animation. We use stochastic progressive photon mapping to render the final photons. The render is split over multiple iterations, each processing a separate batch of photons. For the mapping from source to target, we reuse the continuous bijective map constructed from the first set of photons. To ensure convergence, the kernel density estimation radius reduces in each iteration. In the following videos, there are two examples of our method when used without any additional constraints. In this other example, when blending without caustics, photons from the white caustic mix with the green caustics. Using walls and directed lines, we can avoid the crossings and redirect the photons through the center. Finally, as a post-process, we allow users to add synthetic turbulence to the flow. To construct a turbulent vector field, we compute the curl of a scalar field that was generated by Perlin noise. Using this, we can add multiple synthetic turbulence scales to our vector field and generate fast or slower vortices. The grid used to generate the random vector field influences the size of the vortices that the noise field produces. As a summary, we propose a method to create caustic animations where we blend the caustics to a chosen target image along an unsteady vector field, describing the photon trajectories as particles moving in a fluid. Using this vector field, we can also introduce new constraints that help the artist direct the flow, create boundaries, or add additional effects such as synthetic turbulence. In the future, we would like to accelerate the computation using an adaptive grid that would allow us to compute more detailed flows that take photons closer to their target. It might also be interesting to investigate how controlling motion through a fluid field could be extended to control the movement of water, smoke, or crowds. And that's it for this video. Thank you for listening.
Okay, thank you, Irene, for the very nice work and presentation. We'll go to the Q&A session now. I'll just start with a very simple question. How do you actually define your target, your target for your animations?
So we basically just choose whatever image you want to blend the caustics in, and then we do importance sampling on the image. Since we distribute the energy through the entire image, so each of the target photons have the same energy, and we just like sample the image.
Okay, thank you. So we have a question here. So if I understood correctly, the optimization is currently done by per time step. Do you know if using a global optimization for the entire set of frames could be beneficial in this problem?
So that's an interesting question. So we started doing it per time step because it was natural to the problem, since each time step it's going to change, the constraints can change, you can delete some walls, you can redirect lines, and thus it was easier to do it that way. And it also gives us advantage because you can see it almost in real time, the advection, and if something goes wrong you can just stop and modify the constraints. But one can think that maybe doing it after you set everything, you can solve the entire thing globally, and then I think it would help for the transition at the end, when you have to transition between the vector field that is guiding the photons and the linear, because at the end the vector field doesn't have enough resolution to set the photons exactly to their position. So I think it could help maybe, but I would only do it after you have set up the entire system.
And could you actually think of the reverse process instead of trying to optimize the photon positions? Try to optimize your surface using some goal-based caustic that would change your surface to actually go to where you want.
So this is actually a problem that has already been solved. It's one of the related works, which is basically the inverse problem, and it's been solved where you can actually optimize the surface so that it creates the caustic. But I mean, in this case, it's completely the opposite. So we just want to modify the light instead of having to modify the scene. But yeah, one could do it the other way.
You need to blend from the first surface to the target surface, right?
Yeah, yeah. You would have to modify the geometry, which is slightly more difficult, I would say.
We have another question here. Would it be possible to create caustic animations on curved surface or arbitrary 3D objects?
Yeah, definitely. I mean, any an object that you define as a specular object, whatever form it is, we also created many basic scenes to test the parameters where we just put a blob, whatever geometry, and it works. It will create caustics, and they are really interesting. But in the scenes that are shown in the presentation are more like common objects.
But that's for the object that is actually creating the caustic, right? But you still need to project on some planar surface.
Oh yeah. So in the original paper, they actually they actually project the points in whatever surface you take them in 3D to 2D. In this paper, since it's just like a preliminary work, we just directly take them from a 2D plane. But in the case of the caustics were projected in a 3D object, then you would have to project it to a 2D plane first, do the blending there, and then unproject to the 3D scene.
Okay. We have another question here. Is it possible to animate the speed with which the photons move from the start to the end position?
Yeah, so we basically try to, right now we try to make it from 0 to 1, let's say. The entire thing is gonna go so that at 1 exactly the photons reach the target. But you could also change it by basically adding directed lines, which will make the photons move faster, and as soon as they are close to the target position, they just disappear from the optimization, which means the other photons will be still moving with the vector field, but some of the photons will already have reached the target, so won't move anymore. So you could change the speed of the photons.
Okay, very nice. Just a curiosity, in some image, like the bunny with the bird, maybe it's just an impression, but it seemed that there was more energy at the end than in the beginning. But it's just because they're more concentrated, or
It could
Is it
be,
something else?
it could be depending on the target image. Some of them are more difficult, where there's images with very thin structures, and then the photons have to arrive there without crossing the others, which is the main point of the vector field. So at the end of the animation, they have to really converge, and it looks like there's much more energy because they suddenly need to go to the target position. So that's why I think maybe the global optimization will help there to make it smoother at the end.
Okay, thank you. If
Thank
there are
you.
no more questions, thank you, Irene, again, for the very nice work and presentation. We'll move on to the last presentation, which is conservative ray batching using geometry proxies, which will be given by Matthias Molinar.
Let's start with a quick introduction to path tracing. Imagine we have this scene with a grass field, a tree, the sun, and our camera. The sun emits light onto the tree, and the tree reflects this light into all directions, a small percentage of which goes towards our camera. When that reflected light hits a surface, such as the grass, then it again reflects into all directions, again, a small part of which may reach our camera. Most light never reaches our camera though, so in practice we reverse this process. We shoot rays, starting from the camera, into the scene. When we hit a surface, then we check whether the light source, in our case the sun, contributes light to it. Like we've seen before, we may also receive light from other directions, so we have to shoot a ray into a random direction. If that random ray hits a surface, then we repeat this process of checking for a contribution from the sun and shooting a random ray. We usually limit the number of random rays, or bounces, to prevent an infinitely long path. The easiest way to implement path tracing is by processing one path at a time. We start by generating a camera ray, and then we find the first surface that is hit by that ray. For this, we use an acceleration structure that we have built over the primitives that make up the scene. Usually, this is a tree structure, such as the bounding volume hierarchy. If we hit a surface, then we perform some shading operations. This means that we compute how the surface reflects light, and we test whether the light, the sun in our previous example, is directly visible. As part of the shading step, we also generate the randomly refracted ray, which we then intersect and shade. This may generate another random ray, so we keep repeating this process. This way of writing a path tracer is easy to understand because it nicely maps to our problem. However, it also has some disadvantages. For example, because we operate on only one path at a time, we may not be able to utilize SIMD instructions or GPUs to their fullest. Another issue, which we'll discuss next, is that because of randomly reflected rays, we have incoherent memory access patterns throughout our acceleration structure. This issue of memory coherency is important, so we would like to explain this further using an illustration. Imagine you have an acceleration structure that consists of a tree, and this tree is quite large, so it does not completely fit into our cache. Instead, our cache can only hold 8 nodes at a time. Initially, none of the nodes are in the cache, so we'll mark them as gray. If we want to find the first intersection along a ray, then we need to traverse the tree. When we access a node, it will be loaded into the cache, which we'll visualize by making it green. We keep traversing the tree until we reach a leaf node. A leaf node contains some of the geometric primitives, such as triangles, that make up the scene. We check whether the ray intersects any of these primitives. In this case it does not, so we have to backtrack and traverse another subtree. And we reach another leaf node, so we'll test against its geometry. And in this case the ray does hit, and we are done with this ray. Now we traverse the tree with a second ray, and it has a completely different origin and direction as the first ray, so we'll also take a different path through the tree. We start by visiting the right child of the root node, and at this point we have 8 nodes in our cache, so our cache is full. From now on, anytime we access a new node, we have to evict one of the old ones. We keep traversing, and we reach a leaf, but we do not intersect the geometry at that leaf. So we have to backtrack, and we traverse a new subtree, which requires evicting more old nodes. And we reach another leaf, and we find an intersection, so we are done for this ray. Finally, we have a third ray, that has roughly the same origin and direction as the first one. It also takes a similar path through the acceleration structure as the first ray. However, we have to load all the nodes again, because we just evicted them while traversing the previous ray. This would not have been the case if we would have traversed this ray immediately after the first one. So it is clear that we want to order the rays in such a way that they take roughly the same path through the acceleration structure. This is especially important when it comes to out-of-core rendering. In out-of-core rendering, the scene is too large to fit in system memory, so the system memory has to act like a kind of cache for the hard drive or solid-state disk. So when we refer to a cache miss, this means that the data is not in system memory, but instead has to be loaded from disk. And even a fast NVMe SSD has a latency that is 4 orders of magnitude higher than system memory. So cache misses in the acceleration structure are clearly a big problem. An alternative way of writing a path tracer is a wavefront path tracer. In a wavefront path tracer, we do not process one path at a time, but many paths at a time. We start by generating all the camera rays. Then, we traverse the acceleration structure for all of these rays. Finally, we perform shading for all of the rays that hit something. This process is repeated for all of the random bounce rays. This way of processing large arrays of data maps much better to SIMD instructions and GPUs, and it gives us an opportunity to improve the memory coherency. Ray batching is one of the techniques that we can apply to a wavefront path tracer to reduce the number of cache misses. We start by splitting the acceleration structure into 2 levels, a top level, which is always in memory, and a bottom level, which is either stored on disk or, in our case, rebuilt when needed. The same holds for the geometry, which is also stored on disk. In addition, each leaf of the top level structure has a ray batch. A ray batch stores all of the rays passing through that region of space. To traverse the structure, we first take all of the rays and batch them at the first top level leaf node that they visit. Then, as long as there are still rays in the system, we select one of the leaf nodes. We pick the one with the most rays. We load its geometry from disk and rebuild the acceleration structure. Then, we traverse the rays. Rays that hit the geometry are shaded. And rays that miss are moved to the batch of the next leaf node along the ray. To summarize, ray batching groups rays that travel through the same region of space. A ray is batched when traversal of the top level acceleration structure reaches a leaf node. Since we use a bounding volume hierarchy, this means the ray passes through the axis-aligned bounding box that is tightly enclosing the geometry. Axis-aligned bounding boxes are a very rough approximation of the geometry underneath. Many rays will hit the axis-aligned bounding box, but not hit any of the geometry. Batching those rays is thus wasted work, and it will lead to more disk loads, more acceleration structure rebuilds, and more traversals of those acceleration structures. To illustrate, let's track how the red ray traverses the tree. The ray first visits node 1, where it misses the geometry, after which it will visit node 3, where it does hit. For this example, we assume that we can only fit one node in memory at a time. We start by selecting the node with the most batch rays, in this case node 3. We load its geometry from disk and build the acceleration structure. Then, we traverse the rays through the acceleration structure. All rays hit and we are done with this node. We now have to select a new node, in this case we select node 1. To make space for the geometry and the acceleration structure of node 1, we first have to evict the data from node 3. Now we can intersect the rays and we figure out that the red ray misses and it is moved to node 3. The other 2 rays hit and they are done. Now we again select a new node, which is node 2. To make space, we have to evict the data from node 1. We can now load the geometry and acceleration structure and intersect the rays. They both hit, so they are also done. Finally, we select node 3 again. We have to evict the data from node 2 so we can load the geometry and build the acceleration structure. We intersect the red ray and we are done with the whole system. Please note how we now had to load node 3 twice just because we had to wait for the red ray to first figure out that it misses the geometry at node 1. This problem sparked the idea for our contribution. Instead of storing just the access line bounding boxes, we propose to also store an alternative, more refined representation at each top-level leaf node. It is key that this proxy geometry fully encloses the actual geometry, such that any ray that hits the actual geometry also hits the proxy geometry. We use the proxy geometry as an extra test to determine whether we should batch a ray. We only batch a ray if it hits the proxy geometry. Otherwise, we backtrack and continue traversal. Our proxy geometry consists of a conservatively voxelized representation of the actual geometry. To store it in a memory-efficient manner, we built a sparse voxel octree, or SVO, for each leaf node and compress these SVOs into sparse voxel directed acyclic graphs, or SVDAGs. The idea behind the SVDAGs is that an SVO may contain duplicate information such as equivalent leaf nodes or subtrees, which is a waste of space. We remove these duplicates by replacing them by a single instance. In this example, we have 4 black leaf nodes and 3 white leaf nodes, which means that we have some duplication, which we can remove. Then, we are left with 2 nodes, which both have a white leaf node on the left and a black leaf node on the right, which means that they're also equivalent and could also be replaced by a single instance. To traverse the SVDAGs, we can use most existing SVO traversal algorithms. We use a modified version of the algorithm presented in efficient sparse voxel octrees. So let's have another look at our ray batching illustration. For each top-level leaf node, we now not only store the access line bounding box, but also an SVDAG. When we traverse a tree and we reach a leaf node, we first test whether the ray hits anything in the SVDAG. In this example, it misses, so we continue traversal to the next leaf node. We test again whether it hits the associated SVDAG. In this case it does, so the ray can be safely batched. To test whether adding proxy geometry actually improves ray batching, we implemented a waveform path tracer from scratch. For the top-level acceleration structure, we use a special kind of BVH, which allows us to efficiently store the traversal stack. For the bottom-level hierarchy, we use the Embry ray tracing kernels, which also uses bounding volume hierarchies. And as we just mentioned, the proxy geometry is stored as a sparse-directed acyclic graph. The source code of this project is available on GitHub. These are the scenes that we will be using for testing: the Austrian crown scene, the landscape scene from the physically based rendering book, and the island scene by Walt Disney Animation Studios. For our first test, we measured the construction time of our proxy geometry for the Austrian crown scene, which was subdivided 3 times. We configured our system to generate 151 top-level leaf nodes, which means that we also have to create 151 SVDAGs. In this scene, it took about 10 seconds on a 12-core 24-thread CPU to voxelize the geometry and create the SVOs. Compressing the SVOs into SVDAGs is a single-threaded process, and it took roughly 600 milliseconds. We found that the memory usage of the SVDAGs scales roughly linearly with the voxel grid resolution. Keep in mind that the graph on the right uses a logarithmic scale on the x-axis and a linear scale on the y-axis. The differences between the 3 scenes can be attributed to the different number of top-level leaf nodes. This graph shows the percentage of rays that hit the access line bounding box of a leaf node but do not hit the SVDAG. This shows that over 50% of the rays are batched without hitting any geometry. We also see diminishing returns at voxel grid resolutions of 256 cubic and higher, which is the resolution we will be using for the upcoming results. We can also illustrate the effectiveness using a heat map. Here, the color indicates the number of times that the ray had to be batched. This includes indirect rays. We can determine the performance overhead of our contribution by measuring the render time of 3 different configurations. In all cases, the geometry was loaded and the acceleration structures were built before rendering started. In the first configuration, we measure the render time with normal ray batching. In the second configuration, we traverse the SVDAGs, but we discard the result. Finally, in the third configuration, we traverse the SVDAGs and we use the results to skip batching if possible. The SVDAG traversal on its own adds about 10% to the total render time. However, we can save even more time than it costs us by not having to batch as often, by not having to traverse the bottom level acceleration structures as often. It thus has a negative overhead, not even considering the reduction in disk bandwidth. With regards to the disk bandwidth, we measure a 40% reduction in the bandwidth for the landscape scene. We measured the disk bandwidth at different geometry limits, where the percentage indicates the size of the geometry cache relative to the size of the scene. For the island scene, which is larger and more geometrically complex, we see an even bigger saving. Finally, for the crown scene, the savings are modest. This is to be expected, however, because the complexity of the scene is virtual. The only reason why it is so large is because we subdivided the triangles a couple of times. So let's summarize. We first explained how ray batching aims to improve cache coherence, specifically for out-of-core rendering. In ray batching, rays have to wait until there is a sufficiently large batch, and only then will we load the data from disk and perform the intersection test. If a ray misses, then this wait would have been for nothing. So we propose to store a proxy of the actual geometry, such that we can more accurately test whether a ray might hit something, before we have to load anything from disk. And with just a very low cost of performance, we can reduce the number of times that a ray is to be batched by about 50%. And our results show that it also heavily reduces the amount of data that we have to load from disk, which should equate to lower rendering times. We leave it to future work to test whether geometry proxies could also be used to improve other out-of-core traversal algorithms. We also acknowledge that the intersections with the proxy geometry could be used to sort arrays for improved coherence of the bottom-level acceleration structures. And with this, we would like to conclude our presentation.
Okay, thank you, Matthias. Very nice presentation work. So let me kick off with some questions here. So you define these top level leaf nodes. Actually, how do you define them? How do you choose the number that you put there? I see that it scales more or less with the size of the scene, but is there any way that you can choose this wisely or optimally?
I would say that in this paper we actually didn't do it optimally. So there are basically two choices you have to make. Do you want to balance them such that you have roughly the same number of objects per top level leaf node, or roughly the same amount of memory? Because with instancing that can change quite dramatically. In this case, I tried to go for the same amount of memory, but there's this presentation earlier or yesterday on how to do this called Finding Efficient Spatial Distributions for Restfully Instance 3D Models at the first session of EGPGF. I actually think if we would have implemented that, it would be better.
Okay, and I see that your gain, that is your negative overhead, was kind of constant for all the scenes, right? But all the rest they vary for scene. And how come the performance overhead remains constant?
The cost that you have to make to actually traverse the BVH and load the data can vary quite dramatically between the scenes because of the instancing. And the cost of doing the intersection test with a voxel grid or with the SV deck is roughly the same everywhere. And the cost of batching itself is also roughly the same because it's a queue that you have to add to. So that's because the voxel grid is always the same, roughly the same size. So the voxel grid is the same size, the SVO is dus roughly the same size and thus always have roughly the same cost to traverse. And it's not the case for the actual geometry.
So would it make sense to resize the voxel grid? I mean, the resolution also depending on the scene?
Yes, maybe.
And would also this the same idea work for any other kind of ray tracing algorithms, such as bidirectional ray tracing or things like this? Or would you have to make some modifications for that to work?
Well, you could basically plug it into anything. I plugged it into ray batching here. We could also apply it to normal ray tracing, although I think it only works if you do out-of-core rendering. I'm not sure if the Like negative overhead here is also because ray batching has some overhead. And I'm not sure if it would be negative overhead for like in-core ray tracing. I haven't tested it, but you could basically apply it anywhere.
Okay, thank you. So, if there are no more questions from the audience, this was our last presentation for this session. I thank all the authors and everyone that watched the presentations. I see there were quite some people watching, and if you have more questions, you can reach the authors in the Discord channel for the conference. And I would also like to take this opportunity to thank the organizers for the immense work they had in setting up this virtual conference and the great work. It's going really well so far. So enjoy the rest of the conference, everyone. And with this, I close this session.